Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Mateo. Welcome to our show. Let's talk about physics.
In the 16th episode of this series, let's talk about quantum electrodynamics.
Quantum electrodynamics was the first modern field theory, a new version of relativistic quantum mechanics. It became the template for all current field theories. In Dirac's original model, particles and antiparticles shared states with both positive and negative kinetic energy. Particle-antiparticle pairs constantly emerge from and return to the quantum vacuum. Dirac's C model had an issue. An infinite number of unobservable particles filled the vacuum. A mathematical trick called second quantization transformed quantum waves into quantum fields. Now, particle-antiparticle pairs emerge from and return to quantum fields, resolving the issue. The infinite sea of unobservable particles disappears in quantum electrodynamics.
Anya, I agree with you.
Quantum electrodynamics is the first modern field theory, born from the genius of Dirac. Dirac previously pioneered the use of the Klein-Gordon and Dirac equations for relativistic quantum mechanics. Quantum electrodynamics precisely describes how electrons and positrons interact with photons. It is an extremely successful theory. Tominaga, Schwinger, and Feynman were awarded the Nobel Prize for their contributions. Quantum electrodynamics is inherently quantum, matter-antimatter symmetric with no quantum classical frontiers. Therefore, quantum electrodynamics predicts the existence of an inexistent antimatter world and does not predict the classical nature of macroscopic and cosmological objects.
Dear Mateo, you are well informed.
In experiments, particles and antiparticles always have positive kinetic energy. In Dirac's original theory, antiparticles as common states linked to particles' exotic states. By flipping the kinetic energy sign of an exotic electron-free state, we get a positron's positive kinetic energy. In quantum electrodynamics, particle-antiparticle pairs always emerge with positive kinetic energies. Yet, Feynman diagrams show positrons moving backward in time, a curious mathematical trick. Grave de Peralta's theory aligns more with Dirac than with quantum electrodynamics.
Anya, I agree with you.
In Grave de Peralta's relativistic quantum mechanics, a pair of equations with both common and exotic solutions are used. Imagine transforming these waves into fields through second quantization. It's speculative but promising. We could see a new era of quantum electrodynamics that handles particles and antiparticles with ease, and also might finally address matter-antimatter asymmetry and quantum classical frontiers. It's an exciting topic of research, waiting to be explored and understood.
Mateo, this is an excellent topic of investigation for young theoretical physicists.
Anya, you know a lot. Let's summarize our discussion today.
In the world of physics, there are several takes on relativistic quantum mechanics. The most accepted? Quantum electrodynamics. It transforms quantum waves into fields using a second quantization procedure. Quantum electrodynamics was the first modern field theory. It's the blueprint for all current field theories. These theories excel at describing quantum particles and antiparticles interacting with photons. But they fall short in predicting quantum classical frontiers and observed matter-antimatter asymmetry. Could Grave de Peralta's hypothesis bridge these gaps? Could it introduce quantum classical frontiers and matter-antimatter asymmetry?
Mateo, I think that many young theoretical physics will be tempted to answer this question.
Anya, I hope we will know the answer very soon. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.